This is lecture 3. We'll continue on ray propagation in homogeneous medium, on laws of reflection and refraction, Fermat's principle, and using it to derive these two laws. And we'll look into spherical mirrors. Well, what is ray optics? It deals with image formation, basically following the ray, where is the light ray and what's the direction that it's taking. Now, you'll know that light ray actually points in the direction whereby the optical energy is flowing. And when we talk about ray bundles, then we will be talking about the density of rays that will be proportional to the density of the light energy. Now here, light travels in the form of rays, which we are aware of that. Now, in an optical medium, then we normally characterize it by its refractive index, which is related to the speed of light that's traveling in the medium, and is actually the ratio of the speed of light in free space to the speed of light in the medium. And the time taken for light ray to travel a distance d in the medium then would just simply be given by the distance divided by its speed. So that would then be the optical path length, which is the distance multiplied by the refractive index divided by the speed of light in free space. In a medium, usually the refractive index would be larger than 1, because refractive index in air is equals to 1. Now, in a medium that's not homogeneous, then the refractive index would then be a function of the position, because, for example, traveling from A to B, whereby it passes through regions of different refractive indices. So the medium is of different density. So the optical path length, the total optical path length, then would be a sum of all the optical path lengths that it takes when it travels through this inhomogeneous medium. Basically, it would be the refractive index at whatever position it's at, multiplied by the distance moved, and you take that line integral from A to B. Now, then we talk about how does light propagate in a medium. Well, we have Huygens principle, where it is stated that each point on the leading surface of the wave disturbance, like for in this case is for plane wave, so this is called the wavefront. So on the wavefront, then you have points on it which is taken to be secondary sources of spherical waves, or we call wavelets, whereby they themselves would propagate, would move with speed of light in the medium, and at a time t later, well, v times t, so that the distance that you move, at time t later, now this particular point would have propagated up to here. The wavefront, spherical wavefront would have reached here. This point would have reached here. This point would have reached here, and this point would have reached here. And then when you take the envelope of all these new secondary wavelets at time t later, at this tangent point here, you have this tangent line. So this will form the new wavefront at a time t later. Now, if you have originally a spherical wave, then at every point again, it becomes secondary sources of spherical wavelets at time t later. Then you can then map out a new envelope, and this will be the new wavefront at time t later. Okay, so now, and then how is it used to explain if the wavefront is obstructed by some object? For example, in this case, these wavefronts are traveling through an aperture. So this spherical wave originates from source S, and then it comes to this aperture as S prime. Now we are assuming we are taking light to travel in a straight line, so we are considering rectilinear propagation. So you see here, this will limit and give you the sharp edges of the shadow of this aperture. So you have this line OA and OB. But some wavelength, if you were to draw that wavefront that reaches the aperture, this will be the wavefront. So you'll find that some of these secondary sources on the wavefront would actually have secondary wavelets at a small time t later would have traveled into the region of the shadow. But in Huygens' principle here, in Huygens' construction of explaining propagation of light in this case, these wavefronts that fall onto the shadow region would be ignored. So that's why this Huygens principle has weaknesses, because it did not consider the possibility of diffraction of light into the region in the geometric shadow. And we only talk about the forward wavefront. What about the back half of the wavelets? Now these are all ignored as well, because then it would imply, if we do not ignore, it's implying that we have light disturbance traveling in an opposite direction. So, but these weaknesses were remedied by Fresnel and other researchers later. Huygens' principle can still be applied to prove the laws of both reflection and refraction. Now let's look into Huygens' construction to prove the law of reflection. So we're going to consider an incident narrow parallel ray, and we represent it by these three lines here to represent the ray, and we consider it to be a plane wave. And we have a line here, xy, that will represent a reflecting surface. When this interface xy is not there, then these rays, let's take the wavefront at TEF, would be able to reach this position GHI at time t later. But when this interface is there, this reflecting surface is there, so the time taken for this ray to travel from F to I will be the same as the time taken for this ray to travel an equivalent distance of dg. And then likewise, for this beam, it would be the time taken to travel from E to J plus an equivalent distance of J to H. So to construct a new wavefront, what we do is we will then draw a wavelet for this ray centered at position J. We take this as the radius, we draw the new wavelet, and that will reach up to the medium above. And likewise for this one, this would be centered here, and we draw this wavelet and right up to the top surface. Then to locate where is the new wavefront, we start from point I, we draw a tangential line to all these wavelets that we drew. So this will be the new wavefront. And to represent a reflected ray, then let's take this point D, up to the point where this wavefront touches this wavelet. So that would be the direction of the reflected ray. All right, now let's look at the angles. This is the incident angle, and this would be 90 degrees minus theta I. This angle is equal to this angle from geometry. And this is a right angle triangle. This is also a right angle triangle. They share this side. So then this angle, these two triangles are similar. This angle is equal to this angle. So therefore, we have this angle will be equal to the incident angle theta I, because this is the normal, this is 90 degrees. So and this happened also to be the reflected angle. So we have the incident angle equal to the reflected angle. That is the law of reflection. And of course, when we drew all these rays, it's all in the same plane. So the incident ray and the reflected ray and the normal, they are all in the plane of incidence. Next, we look at Huygens construction to prove the law of refraction instead. So we have the same beam of light represented by these rays, 3 rays here. They are plane waves. So we have the wavefront that has reached DEF, and we're going to take that in this medium, we have a speed equals to VI, and that is given by the ratio of C over Ni, where C is the speed of light in vacuum. And for medium 2, we have a speed Vt, which is equal to C over Nt, which is the refractive index of medium 2. And we are assuming that Vt in medium 2 is slower than the speed of light in medium 1. So Vt is smaller than Vi. Now, the rays at point DEF would then arrive at DJI at different timing. These points are along the interface. And if this medium 2 and the interface XY is not there, then the wavefront GI will be formed when this ray reaches point I. And within that time t that it takes to travel from F to I, then that is to say that when we introduce the medium, then the ray at point D would have entered into second medium, but it is slowing down. So within that time, multiply the speed Vt, it would then have traveled a distance, or rather this would represent the wavelet, a distance given by this wavelet. Let's say we do not know what is the direction of the ray yet. And this ray travel from here to here would be the same, we have taken the same time as this ray to travel from D to G when the second medium is not there. Now with the second medium in place, within that time, it would have traveled from D to this distance. Okay. So now, if we look at this line here, okay, and this line here, so dm here would then be equal to Vt t. And Vt, let's look at t. Now time t here would actually be the time taken for this distance divided by Vi. So then we can then factor out, let's group this together. Vt is actually C over Nt and Vi is C over Ni. So that gives us a ratio of Ni over Nt multiplied by dg. So dm is related to dg through this factor here. Now, likewise, let's look at the middle ray here. We can draw a wavelet from point J with a distance equivalent to Vt multiplied by whatever time is remaining after traveling from here to here. Then we draw an arc. Okay, so now the new wavefront then in the second medium would be obtained by drawing a line that is a tangent, that is tangential to this arc and to this arc. So at the point where it touches, then we will draw a ray from point D to the point where it touched this here M, and for this wave it will be at this point here. So this will be direction of the ray that has refracted into medium 2. So this forms the new wavefront. Now, having said that, we need to find the relation in the angle because we have not come to the complete equation for Snell's law. Now let's look at this angle instead. So we have drawn this ray. So this would be the refracted angle. This one is 90 degrees minus this one. And look at this right angle triangle. If this is 90 minus theta t, this will be theta t. Okay. Next, we're going to look at this angle. This is theta I. This is the wavefront of a parabeam. So this is 90 degrees. So it's 90 minus theta I for this angle here. This is a normal, so this is 90 degrees. So this angle would be theta I. Okay. And then we look at this triangle. Sin theta I is equals to Fi over di. Now this one is common for this triangle, this right angle triangle. Now let's look at theta t. Sin theta t would then be equals to dm over di. Then we take the ratio of sin theta I over sin theta t. That will be equals to this expression divided by this expression. Now you'll find that di cancels off. You have fi over dm. And fi is equal to dg. So we have dg over dm. And we already have worked out that earlier on that dg over dm is actually equals to nt over ni. So there we have ni sin theta I will be equals to nt sin theta t. That will be Snell's law. Another condition is, now if you look at this, the incident ray, the refracted ray, is all drawn on the same plane. And this is normal. So it meets the second condition for law of refraction as well. In Fermat's principle, it can be mathematically expressed as the variation of the optical path length that would yield a minimum. So this is the optical path length where you've taken the line integral along the path of light that has traveled through inhomogeneous medium from point A to point B. In other words, it says that light rays will travel along the path that takes the shortest time, the least time. Now, all those postulates that we have discussed so far, they are used to determine the rules that will govern how light rays propagate. And we have looked into reflection and refraction at interface between two media, and we have looked at transmission through optical component as well. Now let's look at propagation in a homogeneous medium. So if it's homogeneous, then the refractive index and the speed will be the same everywhere. So which means that now for a path that takes the shortest time, that would be a path that would be the shortest. In other words, we have the special case of Fermat's principle, which is called Hero's principle. And to have a shortest distance, basically, it's just a straight line. So light ray travel in a straight line, as was initially also the deduction, because basically when you have an obstacle, you see the sharp shadow. When you have an aperture, again, you see the shadow very sharp. So we can infer that light travels in a straight line. So Hero's principle says that light takes the shortest path when it has to propagate from one point to the other. And let's draw a diagram to prove the law of reflection from Hero's principle. Let's say that the ray will come from source A and will reach source B, and this would be the reflecting surface. And we do not know at which point it will reflect, let's say. So let's put a point which is an equal distance from B, midpoint here, and another point which will be nearer to A and get reflected here. Is that possible? We ask. Another point from A to E and reflects to B. So is that possible? So in order to construct that, what we do is here, so we have already come up with 3 possible paths. Let's arbitrarily take this path ACB. So we will then drop a point which is equal distance perpendicular to this line here, equal distance below the line at A prime. And we then connect A prime to C. So if you look at this, we have a right angle triangle and a right angle triangle. So in other words, this will be equal to this, right? So the distance, if this is indeed the path, then this ray will travel from A to C to B, and it's also the same as traveling from A prime to C to B. Likewise, for all the other points, we do the same. So we can have light coming from here, traveling to D to B, and light from here, traveling to, this would actually be the virtual source, traveling from here to E to B. Now, looking at all this path, the shortest possible path would actually be the straight line. This would be the straight path. So therefore, this would actually be the point where light is going to reflect when it travels from A to B. So then for that matter, now we know that these are similar triangles, so this angle should be this equal to this angle. This is normal. We know this is this is an incident angle. So therefore, looking at this geometry, this angle then would be equals to this angle. So if this is 90 degrees minus theta I, this must be equal to theta I. So we have the law of reflection, theta I equals to theta R. And the normal, the incident ray, and the reflected ray, they all lie on the same plane. So that proves law of reflection. Now let's look at what we did in lecture 2. We actually had the law of reflection, and we also look at law of refraction, that's Snell's law. But we have to take note here that the proportion, how much of reflected light and how much is transmitted through, well, we cannot use ray optics to describe that. It's not possible. Okay, but we can find the location of the ray and the direction that the ray is traveling. Now let's use Fermat's principle to derive the law of reflection. Just now we were using Hero's principle to prove. Now let's use Fermat's principle to derive the law of reflection. So let's say a ray leaves S, strikes the interface at point B, then it will get reflected to some point P. Okay, so from this diagram here, the optical path line would be over here, the refractive index is N, so NSB plus NBP. Now SB, let's say the point where it reflects is at a distance X from this vertical line that comes from S. So this X, so if the total between here to here, the horizontal distance between S to P is A, so this will be A minus X. So we have N, taking Pythagoras theorem. Now this distance would then be H squared plus X squared, and you root that sum. Over here you have A minus X squared plus B squared, and you root the sum, which is over here. So the OPL, which is the optical path length, is a function of X, right? So light will only take the root for which we get a minimum. So what we do is we're going to differentiate this with respect to X. So differentiating with respect to X here, we will then have N multiplied by half. This is to the power of half, so half into H squared plus X squared to the power of negative half, and then you differentiate what's inside, so you get 2x, so that works out to be nx over root of H squared plus X squared. Likewise for this, it will work out to be n into A minus X divided by root of this expression, and we equate that to 0. That is equivalent to writing it as, now, x over hypotenuse is actually sine of this angle. This over the hypotenuse is the sine of theta r. So replacing this and this expression with this and this, we have n sine theta I equals to n sine theta r. For n and n is equal. If this angle is equal, this sine of this is equal to this, therefore this must be equal to this. So therefore we have the law of reflection. Now then, using Fermat's principle to derive the law of refraction, the Snell's law. Well, we can have point A in medium 1 and a point B in medium 2. The ray would travel from A to B, but it is not going to travel along a straight line because it slows down in the second medium. But at which point is it going to enter at the interface? Let's arbitrarily take a point O. Okay, now we're talking about taking the least time, so we have to get the time expression. The total time it takes to travel from A to B will be equal to the time it takes to travel from A to O and O to B. Time taken to travel A to O will then be equal to AO divided by the speed here and OB divided by the speed here. So AO is actually equals to root of A squared plus X squared. So from the notation or distances that we have already denoted in this diagram. And then for OB, and that would be equals to C minus X squaring that term plus B squared, and you root it. Okay, substitute that in. So then what we do is we take the minimum, differentiate t with respect to, because we don't know where's the position, so this is the variable with respect to x. We will then have half 2x into over vi root of a squared plus x squared, and for the other part it will be half into negative 2c minus x over vt root of b squared minus c b squared plus c minus x squared. So you have this cancels, you have x over this expression, and here you have a negative 2 cancels, you have c minus x over this expression. Now if you look back at the diagram, okay, sine of this angle would be x over hypotenuse. Sine of this angle would be c minus x over OB. So sine theta I is x over root of a squared plus x squared, and sine theta t is c minus x over the hypotenuse, which was written by this expression. So dt over dx would then work out to be, now x over this, substitute it with sine theta over vi, sine theta I over vi, and for this expression we substitute with sine theta t over vt. Equating it to 0, it means that this one will be equals to this. Now we are still not there yet. We need to find, substitute this expression with refractive index. So vi would be c over ni. So therefore here will be on this side bt will be c over nt. So both has c cancels out, so you are left with ni sine theta I equals to nt sine theta t. So that is Snell's law. Now in small angle approximation, we can approximate this to theta I, but the angle would be in radians, and this approximated to theta t. We talk about imaging by an optical system. Well, the optical system can consist of reflecting and refracting surfaces that may change the direction of the rays from an object point O. Like you can see over here, you would like to image this object at someplace else. And you have this optical system that is able to, and that can enable you to do the imaging. And this optical system can consist of lenses, mirrors, microscope, or telescope. Now, Fermat's principle implies that every ray that starts at point O and ends at point I, every ray will take the same time to do that. And these rays are called iso, means same, chronos to do with time. So isochronous rays. And the principle of reversibility applies. So which means that if you interchange this becomes object point. This will be the image point. So points O and A are then called the conjugate points. In an ideal system, every ray from the object point that is intercepted by this optical system must pass through that single image point. Then you have perfect image form. But in reality, it's usually non-ideal. Some of these rays may not reach the image point. Why? Because they are lost. Some of the rays lost due to scattering from refracting surfaces, due to reflecting surfaces, and due to inhomogeneity in transparent medium. So what happens is that the image quality is degraded, and there'll be a loss of brightness as well. Another problem would be aberration. This will then, what do we mean aberration here? We are meaning that it is a departure from ideal para-axial imaging. And of course, we also have this problem of diffraction limitation or diffraction limited images. Now, this effect is due to using a limited portion of the wavefront being intercepted by the optical system. Here is an example of technology how to reduce scattering. Just look at one example. This is called a polymer dispersed liquid crystal. This is a trademark. It's called switchable privacy glass. Very interesting. This medium, it has light scattering power that can be adjusted by applying an electric field. So how does it do it? Well, the ordinary refractive index of the liquid crystal does not match the refractive index of the polymer that has been dispersed in this liquid crystal. So incident light that enters will be scattered. What happens is that this material, this sheet of material will become translucent because they get scattered. But when we apply an electric field to it, all these PDLC droplets will then rearrange themselves so that the extraordinary refractive index of the liquid crystal then matches the polymer. And when that happens, incident light can pass through and it changes from translucent to a transparent state. So it is a switchable privacy glass. Let's look into mirrors. Simple example, plane mirrors, which you're all very familiar with. So we have an object here. At equal distance behind the mirror, you can locate the virtual image. Now, we're going to define some Cartesian surfaces. Now, these are surfaces that may be reflecting or refracting, but they can form perfect images. The shape of these surfaces are, for example, parabola. This is a paraboloidal mirror. So all the incident parallel rays that to the axis, they all get focused into a point, the focus point. So this is the concept for telescope, flashlights. We have the elliptical mirror. Now, then we have the foci. So every ray from one of them will reach the other foci. So these are conjugate points, and the rays here are isochronous rays. And we have the hyperboloidal mirror, shape of a hyperboloid. So all these rays from the focal point will be reflected and projecting backward. They seem to come from a virtual point, which is the focus point of the hyperboloid shape, hyperbolic shape. Now, the easiest to make will be the spherical mirror. Unfortunately, when these rays are further away from the optical axis, they will be reflected and will not pass through the same point as the rays which are very near the optic axis. So that is a problem because we will have blurry image here. But normally what we do is we confine rays that are near the axis, so that's why we do para-axial rays imaging. Spherical mirror near at para-axial positions that is close to, they approximates the paraboloidal mirror. So that's why rays that are very near the axis can be brought to a single focus point. And para-axial optics can be called first order optics, and sometimes it's called as Gaussian optics. So by convention, please note that the radius of curvature r, this value r, is taken to have been negative for concave mirror and is positive for convex mirror. Basically, when the center of curvature is on the left side, it will be negative. If the curvature is this way and center of curvature is on the right side, it will be positive. That probably is easier to remember. Let's derive the mirror equation for spherical mirror. We shall consider a convex spherical mirror. The center of curvature is located on the right side of the vertex. That's the point where the surface of the mirror intersects with the optical axis. So we have, let's consider ray 1 that comes from the object at this point here. It is along the optical axis and it hits the mirror perpendicularly onto the surface and get reflected on itself. Projecting backwards, we will have this ray going this way. And then another ray that's inclined at angle alpha coming from the object point O reaches the mirror at point P, and drawing a normal, which is a radial line, we will then have the same reflected angle to the incident angle, and this will be the reflected beam. Projecting that backwards, it will cut the optical axis at point I, and that's where we locate the image that will be intersection between ray 1, which is projected backwards, and this one. And it forms an angle alpha prime here, and point P is at a height of h above the optical axis, and this normal line here will form an angle phi here, and V to R will be R, which is the radius of curvature. O to V is the object distance. V to I is the image distance. And we are considering para-axial rays, so VQ can be neglected. The image is formed behind the mirror, so it is virtual. We have already defined the distances. We would like to derive the mirror equation, which is of this form here. So let's look at this triangle then, POC. This external angle theta is equal to alpha plus phi. Then look at another triangle, which is POI. 2 theta is equal to alpha plus alpha prime. Then we combine these two equations. This one multiplied by 2, and then you minus this equation. You have 2 theta minus 2 theta, that's 0. to alpha minus alpha gives you alpha plus 2 phi minus alpha prime. The 2 phi, bring it on the other side, will give you negative 2 phi. Now, as we are considering small angle approximation, therefore sine phi can be approximated to phi, cosine phi approximated to 1. And let's look at the angles, which is given here. So since we are taking small angle approximation, therefore this angle can be approximated to its tangent value. So alpha can be taken to be h divided by, since we neglect this VQ equated to almost 0, so we can take it as h divided by s, and alpha prime can be taken to be h divided by s prime, and phi here can be taken as h divided by r. So substitute this in, you have this expression, h is common, that cancels out, get 1 over s minus 1 over s prime equals to negative 2 over r. We still have this sign here to take care of because of the sign convention that we are adopting. So to represent convex as well as concave mirrors, therefore we can use a positive sign here, and that will give us the mirror equation. Now, what is the sign convention that we adopted? We assume that light ray is entering from the left, moving towards the right. So the object, if it's real, we have a positive distance, and O is to the left of the vertex. It's virtual if the object is on the right side of the vertex. Then it's a negative value. For the image, it's a mirror, so it should be reflected. It will be real if it's on the left side of the vertex. It's virtual if it's behind the mirror, so it's on the right side of the vertex. The distance will be negative value. Radius of curvature would be positive if C is on the right of V, and negative if C, center of curvature, is on the left of the vertex. Now for plane mirror, which is straight, flat line, R can be assumed to be almost infinity value, and then it will work out that S prime will work out to be negative S, because S prime will take a negative value. It means that it is virtual. Now, in order to remember whether it's virtual or real image, or depending on the mirror and the position of the object, it can be formed behind the mirror, so that's why that becomes virtual. If it's formed on the same side of the object, then it will be a real image. That's one way I use to remember. Let's find the focal point. Now, for a concave mirror, center of curvature is on the left side, R will be negative. So parallel rays from infinity will all fall on the focus point. Okay. To find the object focus, it is defined as taking the limit of S when the image distance is at close to infinity, and you get the focal point. To find the image focus, then you take the limit of the image distance whereby the object is at infinity. So that will give you the image focus point. So this is for a convex mirror. Over here you have object rays coming from infinity, and it get reflected, projecting all backwards. Fine, this is where you locate the image. So if we put the image form at infinity, the object would be at focus point. Substituting that into the mirror equation, this is what we have, or the other way around. Object distance at infinity, image will be formed at the image focus, given this way. So in other words, comparing these two equations, it will show us that F will be equals to F prime, and that is equals to negative R over 2. Okay, so which means that now we can rewrite this mirror equation to 1 over S plus 1 over S prime equal to 1 over F, which is the focal length of the mirror. Now let's then derive the magnification. So what we're going to do is we're going to look at the height of the object and the height of the image. So we have drawn this diagram here of a convex mirror. Let's say we have an object of this height. Just now our object was on the optical axis. Now we extend and give it a height h0. This ray that comes from the tip of the arrow here, if we align it to reach the vertex, then you have this angle equals to this angle, so you can then draw the reflected ray, project it backwards. Another ray which is coming along the radial line to the center of curvature will get reflected on itself. So this is actually drawing the ray diagram. So projecting backwards where they intersect, you locate the image. Okay. So from this diagram here, so this will be the object distance, this is the image distance. So h0, if you look at this triangle, we have this angle equals to this angle, so therefore this angle is actually equals to this angle. So we actually have similar triangle here, the right angle triangle. So h0 over s0 will be equal to hi over si. So lateral magnification basically is the ratio of the image height to the object height. So we have then equal to hi over h0 would then be equal to si over s0. And because of the sign convention that we adopted, basically, then the lateral magnification is actually given by negative si over s0. So this table gives you a list of the value if the value of whether it's positive or negative for the object height and the image height and the magnification as well as the focal length. What does it represent? Okay, you can read through the table, but in order to understand how to use it, it's better that you practice some examples and do some calculation, then you will understand it better. Here gives you, we're going to look at this simple diagram here, try to understand this. This is a mirror, represents a concave mirror. This tells us that now these rays are drawn, they are brought from infinity, brought nearer and nearer to the mirror, and they are at certain height away from the optical axis. When they come from infinity, then they are in front of the mirror, so it will be a real object. Where's the image formed? From infinity, you know that it will be formed at a focus point. And if you look at this distance here, this is shorter, this is longer, so your image is actually smaller. As you come nearer and nearer to the center of curvature, then the image, which is real, which is inverted because of below the line, will then go nearer and nearer to the center of curvature. So when it is at the center of curvature, then the image is still real. It will be the same height, the same size as the object. As you then bring nearer up to the focal point, still a real object, and the image would then grow in size, and it will be formed further and further until it goes to infinity when the object is at focal point. And then you bring even nearer. In this case, the image flipped over, become an upright image, and it will be virtual, it will be formed behind the mirror. These are for concave mirror. And for the convex mirror, nothing interesting. You can bring the real object from infinity up to the surface of the mirror. You will get a virtual image all the time, and it's always smaller. But this is a very useful mirror. The shopkeeper at one corner, and the mirror is up on the wall at another corner of his shop. Then he can view his entire shop if it's properly placed. This is an example of how to make the calculation. We have an object 4 cm height and it's placed 40 cm from a convex mirror and then a concave mirror. There's two questions here basically, each of 20 cm focal length. Find the position and type of the image. So let's start with the convex mirror. For convex mirror, the center of curvature is on the right side. So R is positive, but R is equals to negative 2F, or F is equals to negative R over 2. So F becomes negative. Okay, you're given focal length, so it's negative 20. But the object is real. We assume it's placed on the left side, so it's real 40 cm. So using the mirror equation, substitute value in. So you have 1 over 40 plus 1 over S prime, which you don't know what's that, equals to negative 1 over 20. And it will work out that S prime will be equals to 13.3, negative 13.3 cm. That means it's formed behind the mirror. So there's a negative sign here, means it's behind, it's virtual. What's the magnification, lateral magnification? That's equals to negative S prime over S. So what we have will be negative 13.33 divided by 40 with negative sign in front, so become positive. So it's about 1/3. Yeah, it's positive 1/3. So it's smaller, minified, but it is upright because it's positive, so it's upright. But for a concave mirror, same focal length, place same distance away, but now the focal length is positive. So by changing the focal length to positive, you find that the image now is formed at 40 cm and it's real, it's plus, so it's on the left side of the mirror. Magnification is negative 40 over 40, so it's negative 1, which means that it's the same size as the object, but it's negative, so it means that it's inverted. Okay, we come to the end of lecture 3. So by now, you should be able to state Huygens, Hero's, and Fermat's principle, basically able to explain propagation of light using Huygens principle. And you should be able to apply Huygens principle to prove the law of reflection and the law of refraction. And you apply Hero's principle to prove the law of reflection. You can apply Fermat's principle to prove the law of reflection and refraction. And you should be able to define what's meant by isochronous rays, conjugate points as well, and maybe list some examples of Cartesian reflecting surfaces. Basically, they are surfaces that form perfect images. And you should be able to analyze the mirror system to locate the image, the magnification of the image, as well as determine the nature of the image form. So thank you.